The universe is not a static or motionless place. It never has been quiet. However, for the vast majority of human history, that is precisely what we believed to be true. If you look up at the night sky, the stars do not seem to move at all. The constellations remain exactly the same, night after night and year after year. The moon glides smoothly across the dark expanse. The planets wander slightly, but they always return. To ancient eyes, all of this felt permanent and still, like a massive cosmic painting that had been hung above the world. Consequently, we built our entire understanding of the universe on that perception of stillness. We thought that the Earth must be the center, solid and unmoving. Everything else, the sun, the stars, and the heavens, must be spinning around us. It was seen as a perfect celestial dance, set in motion by something divine, but always repeating in a loop. For centuries, this view held firm, not because people lacked imagination, but simply because it worked. It matched exactly what the eyes could see. It made sense of the changing seasons. It explained eclipses and alignments. It gave us a sense of comfort, a stable world beneath our feet, surrounded by orderly and predictable skies. Shutterstock. Then came a fracture in that illusion. First, Copernicus dared to suggest that the Earth might not be the center after all. Then, Galileo pointed a telescope at the heavens and saw moons circling Jupiter, which was proof that not everything orbited us. And then came Kepler, who studied the paths of planets and discovered they did not move in perfect circles, but rather in ellipses, guided by invisible forces and following precise mathematical laws. Getty images. Ogled bit by bit, the stillness faded away. Today, we know the truth is far stranger than anyone had ever imagined. Space is not silent and fixed. It is in motion everywhere. Not just planets and stars, but galaxies, clusters, and superclusters. Even the very fabric of space is on the move, stretching out in all directions. And yet, we still feel like we are standing still. The ground does not shake beneath us. The stars do not blur past us. The universe feels calm. But that calm is just a trick of scale. It is a mirage. Because the truth is, even now, right this second, we are spinning on a planet, orbiting a star, and flying through a galaxy, all while being pulled by a force we cannot even see. The old picture of a still universe is gone. We have stepped into a story of hidden motion, and we are finally beginning to understand what that motion means. For millennia, the dominant view of the universe had placed Earth at its absolute center. After all, that was what people knew. During the day, they saw clouds glide above them and the sun shine brightly overhead. At night, they saw the moon and the stars stretched out like a giant cosmic painting. Every celestial object appeared to be in motion, and they believed they were at the center of it, all. This view was found across the ancient world, from Chinese sky lore to Mayan cosmology. But it was in the Hellenic world that this idea not only became an accepted myth, it was structured into a technical cosmological model, and the man who did that was Claudius Ptolemy. Ptolemy lived in Alexandria around the 2nd century Common Era during the height of Roman Egypt. He was a scholar, a mathematician, and more than anything, an astronomer who wanted to make sense of the skies, not just philosophically, but with numbers. He inherited a rich tradition from Babylonian star catalogs, Egyptian astronomy, and Greek geometric modeling. But what he did with that knowledge was something monumental. He compiled, organized, and refined it into a systematic model of the cosmos, laid out in a massive work known as the Almagest. The work was so influential that it became the definitive guide to the universe for over 1,000 years. In Ptolemy's model, Earth sat at the very center of the universe, perfectly still and unmoving. Around it, in concentric spheres, revolved everything else: the Moon, Mercury, Venus, the Sun, Mars, Jupiter, Saturn, and finally the sphere of fixed stars. Beyond that lay nothing humans could know. The entire cosmos was a giant set of nested spheres, perfectly ordered with Earth as the pivot of all celestial motion. Each celestial body was embedded in a transparent crystalline sphere that spun smoothly around us. The stars were affixed to the outermost shell, which rotated once every day, giving us night and day. This was not just a random guess. Ptolemy used observations to make his model mathematically functional. He believed the heavens must move in perfect circles because the circle was the most perfect shape in Greek philosophy. But that created a problem. When people tracked the planets over time, especially Mars, Jupiter, and Saturn, they noticed strange behavior. Sometimes a planet would slow down, stop, and even move backward in the sky before resuming its forward path. This retrograde motion made no sense if all the planets moved in simple circles around Earth. To fix that, Ptolemy introduced epicycles. These were small circular paths that each planet traveled, while that entire smaller circle orbited Earth along a larger circle called the deferent. So a planet did not just circle Earth. It circled a point that itself was circling Earth. This looping motion could recreate the backward steps seen in the sky. But even that was not enough. The math did not quite line up with what astronomers observed. So Ptolemy introduced another tweak: the equant. This was an imaginary point slightly off-center from Earth. He claimed that if you measured the planet's motion from this equant point, the movement appeared uniform, not from the actual center, but from this offset position. The model had been refined for centuries, polished and preserved. It had shaped calendars, timekeeping, astrology, and religious worldviews. It had served empires and guided scholars. It had explained the skies for over 1,000 years, but no amount of complexity could hide the truth forever. Observers were beginning to ask hard questions. A few began looking for a simpler explanation. And one name stood out, a name whose revolution still echoes to this day. It all began quietly in 1543 with the publication of a book that would shake the foundations of astronomy. Its title was De Revolutionibus Orbium Coelestium, or On the Revolutions of the Celestial Spheres, and its author was not some famous scientist or thinker. He was a priest. His name was Nicholas Copernicus. That might sound odd today, but back then it made sense. The church was the epicenter of intellectual life in Europe. If you wanted to study mathematics, astronomy, or philosophy, the church was where you did it. Monasteries and cathedral schools were the libraries and laboratories of their time. Born in what is now Poland, Copernicus studied law and medicine, dabbled in economics, and became fluent in Greek and Latin. But his real passion was the sky. And for years he had been quietly collecting observations, running calculations, and writing out an idea that had been forming in his mind. One that went against everything he had been taught. His idea challenged the entire system people believed in. So he kept it mostly to himself. For decades he hesitated, knowing the risks, not just scientific criticism, but religious and political backlash too. Near the end of his life, he finally published that idea reluctantly. In it, he outlined a model of the universe where the sun, not the Earth, was at the center. The Earth, he said, was a planet just like Mars and Jupiter, and it orbited the sun once a year. But he did not stop there. Based on his observation, Copernicus proposed 3 distinct motions of Earth. First, Earth rotates on its axis every 24 hours. That daily rotation is what makes the stars appear to rise and set across the sky. Second, Earth orbits the sun once per year. That revolution around the sun explains the changing positions of the planets and the seasons. And third, Earth wobbles slightly, tracing a small circle while it moves through its orbit, a motion we now associate with the tilt of Earth's axis and the phenomenon of precession. These ideas were not just guesses. Copernicus spent decades developing complex geometric models and astronomical tables. He used trigonometry to calculate the relative distances of the planets from the sun. He ordered the planets based on how fast they appeared to move across the sky. The closer a planet was to the sun, the faster it orbited. That lined up beautifully with what he saw. But even though Copernicus's model made conceptual sense, it did not improve accuracy. That is because he still assumed planets moved in perfect circles just like Ptolemy. And that made his predictions only about as good as the old system, and in some cases, worse. Then came the telescope. It was not invented by a scientist. Actually, it started as a Dutch novelty, just a few lenses slapped together by spectacle makers. But when news of this strange device reached Italy, one man saw more than just novelty. Galileo Galilei. He did not invent the telescope, but he turned it into a scientific instrument. In 1609, Galileo pointed it to the heavens, and what he saw would rattle the old order. First, he looked at the moon through the eyepiece. It was not the perfect, smooth, divine orb that the ancients had believed. It had craters, mountains, and shadows. It looked a lot like Earth. Then he looked at Jupiter, and there, dancing around the planet, were 4 small points of light. Night after night he tracked them, and they changed position but always stayed near Jupiter. These were moons orbiting something other than Earth. This was a huge discovery because the geocentric model claimed that everything had to orbit Earth. But here was Jupiter stealing that spotlight with its own system of orbiting bodies. Then he turned to Venus, and that sealed it. Venus went through phases like the moon. Sometimes it appeared full, sometimes it was just a crescent. And that only made sense if Venus was orbiting the sun, not Earth. If it circled Earth, you would only ever see it in one phase. But if it circled the sun, and we were moving too, then the geometry worked. That little glowing dot proved Copernicus had a point. But Galileo was not the one who finally cracked the math. That fell to someone else. Someone who did not even believe in Copernicus at first. Johannes Kepler was a German mathematician and astronomer, deeply religious, deeply curious, and painfully precise. He got his big break when he became an assistant to Tycho Brahe, the last great naked-eye astronomer. Brahe was a Danish nobleman who spent decades collecting the most accurate measurements of planetary motion ever made, all without a telescope. He built giant instruments in his observatory on an island and charted the positions of planets with mind-numbing precision. Now, Brahe did not buy into the Copernican model. He had his own hybrid theory where planets orbited the sun, but the sun orbited Earth. He tried to split the difference, but when he died in 1601, he left all of his data to Kepler, and Kepler dove in. He spent years trying to make the Copernican system match Brahe's data, especially regarding Mars. And Mars was tricky. It does not move in a nice, simple circle. It speeds up and slows down and loops across the sky. It just would not behave. For years, Kepler tried to force the data into circular orbits. That is what everyone assumed. Circles were divine and perfect. The heavens had to move in circles. But Mars did not care about philosophy. So finally, Kepler stopped forcing the math. He let the data speak. And what it said changed everything. Kepler discovered that planets do not move in perfect circles at all. They move in ellipses. That was his first law. All planets move around the sun in elliptical orbits, with the sun at one focus of the ellipse. This means that a planet's path is not a perfect circle, but rather an oval shape. Kepler also noticed something else. Planets do not move at constant speeds. They sweep across space faster when they are closer to the Sun and slower when they are farther away. That is his second law. A line connecting a planet to the Sun sweeps out equal areas during equal intervals of time. In other words, as a planet moves along its elliptical orbit, the area it sweeps out in, say, a month, is always the same, whether it is near the Sun or far. This explained the strange speeds of planets, especially Mars. And then came the third law, the one that stitched the entire system together, also known as the law of periods. Kepler found that the square of the orbital period of a planet is directly proportional to the cube of the semi-major axis of its orbit. In simpler terms, the further a planet is from the Sun, the longer it takes to complete one orbit. And this relationship is predictable. Together, Galileo's telescope and Kepler's equations did something extraordinary. One gave people the vision to see a new universe. The other gave them the math to prove it. Copernicus had started the fire. Galileo fanned the flames. And Kepler built the framework that finally made it hold. After the door opened, it did not take long before others walked through it and pushed even farther. The next generation moved to the next questions. Why do planets move at all? What force keeps them in orbit? Why do they not fly off into space or fall into the Sun? That is where the famous falling apple came in. Newton gave this invisible force a name: gravity. He realized that the same force that made apples fall from trees also held the moon in orbit, kept Earth circling the Sun, and ruled the dance of planets. He formulated it into a law: universal gravitation. According to him, every object with mass pulls on every other object, and the bigger the mass, the stronger the pull. The farther apart they are, the weaker the pull. Using Newton's law of universal gravitation, we knew that Earth orbits the Sun at about 107,000 kilometers per hour. That is nearly 30 kilometers per second. Mercury moves even faster, around 47 kilometers per second, because it is closer to the Sun and feels a stronger gravitational pull. Mars, being farther out, moves slower. Everything fits together. The closer a planet is to the Sun, the faster it has to move to stay in orbit. Newton's math proved it. He connected the motion of the heavens with the motion here on Earth. For the first time in history, we had one set of laws that applied to everything. And just like that, the great cosmic mystery of planetary motion, why they move, how they move, and how fast they move, was no longer a mystery. It was gravity. But there was something else, something no one expected. Because as scientists charted the heavens with better tools and sharper math, they noticed another motion, a bigger one, a deeper one. The Sun, the thing we thought was at rest, was not. It is also moving. But where? After the Copernican revolution, the Sun took the Earth's place as the center of everything. No longer did the cosmos revolve around us. Now it was the Earth that moved, spinning on its axis and orbiting the Sun. This idea felt revolutionary. But once the paradigm shifted, the new model, the heliocentric one, began to settle. The Sun, once seen as just another object in the sky, became our still point, the anchor of the universe, solid and motionless. And for a few hundred years, that idea held. But that would change. Not with a physicist, not with a philosopher, but with a musician. William Herschel was born in Germany and moved to England as a composer. But he had an obsession: telescopes. He started building them in his spare time, grinding mirrors and designing optics better than almost anything else of his time. And when he pointed those telescopes toward the heavens, he did not just look, he counted. Herschel became obsessed with structure. If the sky was filled with stars, were they scattered at random or was there a pattern? He decided to find out the hard way. He and his sister Caroline began a massive survey. He would count stars in narrow slices of the sky, just a few degrees wide, and note how many he could see in each direction. Over time, these counts painted a picture. He noticed something strange. Some directions had far more stars than others, and the highest density lined up with that faint band we call the Milky Way. So he made a map based on his star counts. He constructed what he thought was the shape of the universe, and it looked like a flat, stretched-out disk, like a grinding wheel with the sun roughly near the center. Today, we know he got the size wrong. He did not account for interstellar dust, which blocked many distant stars from view. But for the late 1700s, this was extraordinary. He had figured out that the stars were not infinite. They were part of a structure, a system, and we were inside it. He called it the galactic system. But Herschel did not know it was a galaxy in the modern sense. He thought this system was the entire universe. He did not realize that those fuzzy patches of light, those so-called nebulae, were actually other galaxies unimaginably far away. Still, what he did see was revolutionary. He showed that we were not at the center of everything, not even close. And that flat shape, it meant something. It suggested structure, motion, and orientation. If the Milky Way had a shape, then we had a location. If we had a location, then maybe we were also in motion. That is when people started asking a deeper question. Where are we really? And how can you tell what is moving and what is not? Because if everything is moving, how do you know when something is still? That is when we hit a wall, not a wall of data, but a wall of perspective. Because everything we see from here, from Earth. Our eyes, our telescopes, our instruments, they are all sitting on this spinning rock that is itself orbiting the sun, which, as Herschel suspected, might be moving too. So, how can you tell what is really moving and what is not? That is where a frame of reference comes in. Let us try a simple thought experiment. Imagine you are sitting in a train. You are sipping your coffee and reading a book. Out the window, you see another train next to yours. For a moment, it looks like that train is sliding backward. But then, wait, are you moving? Or is it moving? Or are you both moving? Here is the thing. Without seeing the ground, you cannot know for sure. That is the trap of your frame of reference. From inside the train, everything feels still. The coffee stays in the cup. The book rests calmly on your lap. But to someone standing on the platform, you are flying by at 80 kilometers an hour. So, who is right? Well, actually, both are, because motion is not absolute. It is relative. And when your only window to the cosmos is from inside that moving train on a spinning Earth, orbiting a star that is moving too, untangling what is really in motion becomes a puzzle. A puzzle that one man quietly and patiently set out to solve. Jacobus Kapteyn never saw himself as a revolutionary. He was quiet, careful, a man who loved numbers more than noise. But what he did with those numbers changed our understanding of the universe. Kapteyn was born in the Netherlands in the mid-19th century. By then, Herschel's star maps were already over a century old. The idea that we were inside a star system, what we now call the Milky Way, was accepted. But the structure, the motion, that was still a blur. Telescopes were better, but astronomers did not just need better tools, they needed a new approach. That is what Kapteyn brought. He started collecting data. Not just light, not just position, but proper motion, how stars shift across the sky over time. These were tiny changes, often fractions of an arc-second per year, but with the right math and enough time, they told a story. He gathered observations from observatories all over the world: the Cape in South Africa, Cordoba in Argentina, and Sydney in Australia. Bit by bit, he compiled star catalogs, thousands of them, measured their brightness, measured their position, watched them drift, and then something strange showed up. The stars were not just drifting randomly, they moved in patterns. Two general streams, like cosmic currents, seemed to flow across the sky. At first it looked like the stars were grouped into two large rotating swarms, but Captain thought harder. What if this was not about the stars at all? What if we were the ones moving? Back to the train analogy. Imagine you are in the middle of a crowd, walking steadily through a busy plaza. People seem to be flowing past you in different directions. But maybe it is you who is the one in motion, and everything else only appears to drift because of your frame of reference. Captain then made the leap. He ran the calculations and it all fit. The pattern of star motion only made sense if the sun was moving and dragging us along with it. This motion came to be known as the solar apex. According to Captain's results, the sun was headed toward a point in the constellation Hercules at about 20 kilometers per second. Not a blazing sprint, but a steady, silent drift through space. And with that, the sun lost its stillness. But Captain did not stop there. He wanted to go bigger. If we are moving through the stars, then what is this collection of stars? What is the shape of the system we are inside? Using the motion and brightness of stars, Captain began constructing what he believed was the true shape of our star system. He assumed stars were distributed evenly in space and that their brightness faded with distance. Based on that, he came up with a model. It looked like a flattened disc-like structure, about 40,000 light-years in size. And in this structure, the Captain universe, the sun, sat near the center. It was our first real attempt to map the Milky Way as a whole. Of course, we now know Captain's universe was too small. He did not know about interstellar dust, microscopic particles floating between stars that absorb and scatter light, especially in the direction of the galactic plane. This dimmed faraway stars and made them look closer than they really were. So, his model underestimated both the size and shape of the galaxy. But for its time, it was groundbreaking. Then came a turning point. Astronomers began to wonder about those faint, blurry spots in the sky, the so-called spiral nebulae. Some believed they were part of our Milky Way, but others suspected something more dramatic, that these might be entire star systems of their own. That is where Edwin Hubble enters the picture. Using the Hooker telescope on Mount Wilson, then the most powerful telescope on Earth, Hubble focused on one of the most prominent of those nebulae, Andromeda. In 1923, he spotted something crucial inside it, a kind of star known as a Cepheid variable. These stars brighten and dim in a predictable pattern, and thanks to Henrietta Swan Leavitt's earlier work, that pattern could be used to calculate how far away the star really was. The answer stunned him. Andromeda was not just far, it was way beyond the edge of the Milky Way. So far, in fact, that it could not possibly be part of our galaxy. This was a massive shift. For centuries, we thought the Milky Way was the entire universe. But now, it was just one galaxy among many, a single island in a vast cosmic sea. But here is what really matters. By studying these other galaxies, we began to see our own more clearly. You cannot look at the Milky Way from the outside. We live inside it. It is like trying to map the shape of a forest from the base of a single tree. But with Andromeda and other galaxies, we finally had something to compare it to. We could look at galaxies from the outside and ask, does our galaxy have a spiral structure like that one? Does it have a central bulge, a flat disk, a halo of stars? Over the next decades, Astronomers used this mirror effect, comparing external galaxies to what we could observe from within the Milky Way. They mapped gas clouds, star clusters, and the distribution of various stellar populations. They used radio astronomy to see through the dust that blocked our view in visible light. Gradually, a new picture emerged. One of them was a Dutch astronomer named Jan Oort, who took a closer look at the motion of stars near the sun. He was not just interested in where stars were, but how they moved. And what he found was strange. If the Milky Way was rotating like a solid wheel, every star should be moving at the same angular speed, just like the spokes on a bicycle wheel. But they were not. Some stars were lagging behind. Some were moving faster. It looked more like a whirlpool than a wheel. Oort crunched the numbers and realized the galaxy rotates, but not evenly. It rotates faster near the center and slower at the edges. He worked out the math behind this and came up with two constants that described the way stars moved near our position in the galaxy. These constants, now called the Oort constants, gave the first real description of the Milky Way's differential rotation. From that, he calculated that our Sun is about 30,000 light-years from the galactic center and moving at an astonishing speed of over 200 kilometers per second. That is fast enough to circle the Earth 7 times in a single minute. At that speed, the Sun takes roughly 225 million years to make one full orbit around the center. That is one galactic year. Shutterstock. And the Sun is not alone. Every star you see in the sky is doing the same thing, spinning around the center of the galaxy like bees around a hive. We just do not feel it because we are all moving together. But if that is the case, what exactly are we orbiting? To answer that, astronomers needed better eyes, ones that could see beyond the visible light. So they turned to radio waves. Specifically, they began mapping out the faint natural radio signal given off by neutral hydrogen atoms. At a wavelength of 21 centimeters, this signal could pierce through the thick clouds of dust that made optical observations nearly impossible. By tracking this signal, astronomers began to map the spiral arms of the Milky Way from the inside. It was like trying to draw a picture of a forest while standing inside the woods. But now they had the tools to do it. And then came one of the biggest leaps forward, the Very Long Baseline Array, or VLBA. The VLBA is not a single telescope. It is a system of 10 radio antennas spread across thousands of kilometers. Imagine placing 2 telescopes on opposite ends of the Earth. Say, one in Hawaii and one in the Virgin Islands. Now imagine syncing them so perfectly they act like one giant dish the size of the entire continent. That is essentially what the VLBA does. It links 10 radio telescopes scattered across the Western Hemisphere to form one super instrument capable of resolving incredibly small movements in the sky. And by small, we are talking about shifts so tiny they are measured in micro-arc seconds. That is like spotting a coin on the moon from Earth. They used this system to track cosmic beacons called masers. These are not lasers you can see with your eyes. They are radio signals naturally emitted by gas clouds around newborn stars. These masers act like lighthouses in space, bright, compact, and perfect for tracking. Because they are locked to specific regions within our galaxy, they help us pinpoint both position and velocity. Over years of observation, astronomers watched these masers inch across the sky. They measured their change in position, that is, proper motion, and also how their light shifted toward red or blue. That is radial velocity, whether it is coming toward us or moving away. Combine those and you get a full 3D picture of motion, not just left and right, not just forward and back, but the whole dance of stars across the Milky Way. And what did that dance reveal? It showed the stars orbiting the galactic center, but not in perfect circles. Their motion forms a spiral pattern twisted and stretched by the pull of gravity and the structure of the galaxy itself. Some arms lead, others trail behind, clusters wobble, gas clouds shear under tidal forces. But there was something else too, something strange at the heart of it all. As these massers and other stars were tracked closer and closer to the galactic center, something became obvious. Their speed increased dramatically. Objects orbiting near the center were whipping around at insane velocities. But here is the kicker. There was not enough visible matter there to explain that kind of gravity. There were stars, yes, dust, gas, but not nearly enough to hold things together at those speeds. Something invisible was anchoring the galaxy. And all that motion, all that math, all those precise measurements, they all pointed to the same place. A compact, dense radio spot near the constellation Sagittarius. That spot is known as Sagittarius, a star. It does not look like much in visible light, just a haze of dust and stars. But in radio wavelengths, it lights up. VLBA observations zeroed in on it, and what they found was a motionless object, relatively speaking, that everything else was spinning around. Its mass was over 4 million times that of the Sun. Its size is smaller than the orbit of Mercury, the only thing in physics that fits those numbers. That small, that dense, that massive is a black hole. A supermassive black hole. That is what anchors the Milky Way. It sits quietly in the center, barely flickering, while every star, every planet, every gas cloud in the galaxy swirls around it. And still, we are not standing still because the stars are not just orbiting around the center. The entire galaxy is twisting, warping, and wobbling. One of the arms we are riding on, the Orion Spur, gently rises and dips above the galactic plane like a surfer riding a wave. But even the Milky Way is not standing still. Our entire galaxy is in motion, drifting, pulled by unseen forces. A car comes racing toward you, its engines roaring, and just as it passes, it changes pitch, higher as it comes in, lower as it drives away. That is the Doppler effect. It happens when something that makes waves, like sound, moves toward or away from you. When it is coming closer, the waves bunch up. When it is moving away, they stretch out. Light does the same thing. If a star or galaxy is moving toward us, its light waves get squeezed, shifted slightly toward the blue side of the spectrum. We call that blue shift. If it is moving away, the light gets stretched. It shifts toward red. That is redshift. In the 1910s and 1920s, scientists started using this trick to measure the motion of stars and galaxies. One of them was Edwin Hubble, and what he found was shocking. Most of the galaxies he observed were not sitting still. They were moving away from us, and the farther away a galaxy was, the faster it was receding. Some were flying away at hundreds of kilometers per second, others thousands. Hubble mapped this out, and with each new galaxy, the pattern held up. Farther meant faster. Space itself was expanding, and the galaxies were just along for the ride. It was one of the biggest discoveries in the history of science. It meant the universe had a beginning. It meant everything we see today used to be much closer together. It even laid the groundwork for the Big Bang theory. But not every galaxy is running away. There was one that stood out, a familiar neighbor, big and spiral-shaped, the Andromeda galaxy. In 1912, an American astronomer named Vesto Melvin Slipher pointed his telescope at Andromeda and measured its light spectrum. At the time, people were just beginning to understand how redshift and blueshift worked with galaxies. and what Slifer saw went against everything they expected. Instead of being red-shifted like most galaxies, Andromeda's light was blue-shifted, meaning it was heading toward us. But back then, that was all they could really say. Just a direction, not the full picture. Fast forward 100 years, technology has come a long way. We have got space telescopes, supercomputers, and a whole network of radio dishes spread across the Earth. Astronomers use data from NASA's Hubble Space Telescope, combined with precise measurements from the Gaia mission and the VLBA. By tracking the actual movement of Andromeda over many years, not just the light shift, but its sideways motion too, they pieced together a full 3D map of its trajectory. And what they found confirmed it. Andromeda is not just drifting near us. It is not going to slingshot by. It is locked in. It is on a direct collision course with the Milky Way, and we are heading toward it, too. It is not just that Andromeda is coming for us. We are both racing toward each other across the void of intergalactic space. Right now, Andromeda is moving at about 110 kilometers per second in our direction. That is over 400,000 kilometers per hour. And the Milky Way is not sitting still either. We are drifting toward Andromeda at nearly 300 kilometers per second when you factor in the motion of our whole local group of galaxies. That means the gap between us is closing fast at roughly 500 kilometers per second when you add it all up. Still, space is big, really big. Andromeda is about 2.5 million light-years away from us. That is roughly 24 quintillion kilometers, a number so huge it barely feels real. At that rate, even with both galaxies barreling toward each other, the closing speed is not enough to make it happen anytime soon. So, no, not tomorrow, not next year, but in about 4 to 5 billion years, the two largest galaxies will finally meet. Now, you might picture this as a galactic car crash, stars smashing into stars, chaos, and fire everywhere. But that is not how this works. Galaxies are mostly empty space. The stars inside them are incredibly far apart. On average, the distance between stars in our part of the Milky Way is about 4 to 5 light-years. That is nearly 40 trillion kilometers. Even in the denser core regions, stars are still typically separated by about a light-year or more. To give you a sense of scale, if a star were the size of a ping-pong ball, the next closest star would be several hundred kilometers away. So even during a head-on collision between two galaxies, most stars just drift past one another without ever touching, like ships passing in the night. Still, it is not completely peaceful. A few stars might actually collide, especially in the crowded central regions. And a small number, especially ones on the outskirts, might get flung entirely out of the galaxies, tossed into intergalactic space like cosmic castaways. But the real drama happens through gravity. That invisible force stretches and warps the galaxies. It flings out long tidal tails, streams of stars pulled far from their homes. It rips apart spiral arms. It pulls the cores closer and closer together until the two galaxies finally merge into one larger, messier system. But the full collision doesn't happen all at once. The first encounter is fast, a close pass that starts the chaos. But the merger itself, that is slow. It takes about 1 to 2 billion years to fully settle. It is not a crash. It is a slow, graceful gravitational ballet. And when the dance ends, something new is born, a single massive elliptical galaxy. Astronomers already gave it a name, Milkomeda. It will not look like a spiral anymore. It will be puffier, rounder, a huge glowing ball of stars, gas, and dust. Our sun, assuming it survives, will likely find itself in a new orbit. Not where it is today, not in a neat spiral arm. it could drift farther from the center in a path more elliptical and erratic than it is now. But the collision with Andromeda is not the whole story. It is not the only trajectory our galaxy is on.